Hello everyone, welcome to Mastering Math and thank you for watching. This video series has been designed and developed by the Elsa McGill Learning Center Scholars in the Faculty of Engineering at Carleton University. My name is John O'Keefe and I'll be your host for this high school math review. I recently graduated from Carleton University with a Master's of Applied Science in Aerospace Engineering. In addition, I've worked in the LC Center for the past 6 years helping first-year engineering students such as yourselves. This math review, it's intended to refresh your memory based on high school math topics that you'll be seeing throughout first-year engineering courses. This is meant to be a supplemental resource, so it's not meant to replace any of your in-class learning activities. New students are expected to view this video series as well as read the accompanying PDF document in the link below, and then please revisit this as needed throughout the academic term. And with that, we'll get started. So in this video, we're going to cover derivatives. Derivatives are useful throughout engineering to determine rate of change. Specifically in first year, you're going to need derivatives in mechanics to determine the relation between shear moment and bending moment in the circuits course. So that's the relation between charge and current. And then finally in dynamics course. So that's going to be your relation between position, velocity, and acceleration. So with this, we're going to start off with some theory, then we'll get into the rules and laws of derivatives, and then just the applications which I just discussed. So starting off with the theory, if we have a function here, just draw it as a curved line like this, and this is f of x. Now, similar to our last video, the rate of change, we can draw a line tangent to the curve here. And we want to determine what the rate of change of this line is. So that's the same idea as getting the slope of that line. So your rate of change is just going to be equal to your rise over your run. But now this time, rather than considering x or x plus h, we're going to consider a delta x, or in this case, it's actually a dx, so a very small slice, very, very small dx, a differential in x. And over that change in x, we have a differential change in y. And that's known as dy. So then we could evaluate what the rate of change of this is by your rise, which is dy, divided by your run, which is dx. And this is derivative notation. This is referred to as Leibniz notation. And this is how you can refer to a derivative as. So another method of referring to a derivative is also f prime of x, which you've probably seen before. That's the exact same thing as this dy by dx, where the dy by dx just shows it's the rise over your run, your differential rise, y, versus your differential run, x. And this could also be referred to as the differential, so the change in your function, f of x, divided by the change in your x. All three of these are saying the exact same thing. They're just in different notations. So now that we got through that, we can go through some rules and laws here. So I'm going to start off with functions. So this is going to be f of x. And on the right side here, I'm going to have what their derivative is, f prime of x. So we just start off with a constant c. The derivative of a constant c, that's just 0. If we then consider a line, so ax, the derivative of ax is simply just a. If we consider a quadratic, so this would be x squared, the derivative of this is 2x. Then keep going, we have an exponential, so e to the x. The derivative of e to the x is e to the x. It just repeats itself. Next we have ln of x, so the inverse of e to the x. The derivative of this is 1 over x. Next up we have sine of x. The derivative of this is cos x. And finally we have cos x. Scroll down a bit. So we have cos x here. And the derivative of that is negative sine x. There's a few more derivatives that I cover in the PDF document in the link below. But that's all I'm going to cover here right now. So now the next part is laws. So this is referring to like your chain rule, your product rule, and everything like that. So here, if I have rule, and then in blue, I'm going to write the derivative. So first up, we have the power rule. So this is x raised to the power of n. So power rule, we bring the exponent down, so this becomes n x, and then we decrease the power by 1. So then this is n minus 1. Next up, we have summation rule. So this is f of x plus g of x. The derivative of this, we can just take the derivative of them each separately. So this becomes f prime of x plus g prime of x. So next up, scalar multiplication. So if we have a function, f of x multiplied by c, we can then just take the derivative of f of x and just leave c out front. So all of these functions, f of x or g of x, they could all be just these functions listed here. And this could be e of x, ln of x, sine of x, cos of x. They don't need to be large expressions. All of these right here are functions. So now getting into a couple trickier ones. We have product rule now. So this is when two functions are multiplied by each other, f of x, g of x. And then the derivative of this, I'm going to take the derivative of the first, then leave the second the same, and then I'm going to add. Now I'm going to leave the first one the same, and I'm going, sorry about that, I'll redo this part. So we'll do this in blue. So we take the derivative of the first, leave the second the same, then we add, we leave the first the same, f of x, and then we take the derivative of the second, g prime of x. And you can do this in either order. Since it's summation, it can be in either order. So next up, I'm going to do quotient rule, f of x divided by g of x. So this is, just got to make sure to get the order correct. In this case, it does matter. So we have f prime of x, g of x. So we take the derivative of the first, leave the second the same. Next, we take the derivative of the bottom, so g prime of x, and we leave the top the same, f of x. And then we divide all of this by the bottom squared, so g of x squared. And that is quotient rule. And now finally, we have chain rule. So this is where we have a function inside of another function. So we have f of g of x. So this becomes, we take the derivative of the outside. So this is f prime of g of x. And then we multiply this by what the derivative of the inside is. So this is g prime of x. And those are all the rules that we're going to cover today. So now we'll do a couple practice problems with these rules. So if we have a function f of x is equal to 2x squared plus 5x plus 1, we can evaluate the derivative of this as f prime of x is equal to, we can treat them all separately as the summation rule says, and we just apply power rule. So this becomes 4x plus 5. Another example. So this is going to be example 2, and this is our example 1. This becomes f of x is equal to sine x plus e to the x. Now evaluating what the derivative of this is. The derivative of sine x is cos x. And then the derivative of e to the x is e to the x again. And that's it. So a third one here, example 3, we have y is equal to sine 2x squared. And now using this notation, the Leibniz notation, we can evaluate this as dy by dx. So the change in y with respect to x is equal to sine 2x squared. So this is chain rule. We're going to take the derivative of the outside. So cos 2x squared. And now the derivative of the inside would be 4x. And that's that one. And finally, the last one that we'll do, example 4, we have y is equal to ln of cos of 3x squared. So we have essentially three functions here, and we'll have to apply the chain rule twice. So using the Leibniz notation again, so dy by dx is equal to the derivative of ln is 1 over. Then we keep everything inside the same. So 1 over cos 3x squared. Next, the derivative of cos 3x squared, that's going to be negative sine multiplied by, and we leave the inside the exact same, 3x squared. And now finally, we take the derivative of the inside, which is 3x squared, and that becomes 6x. So now we'll just clean this up a little bit, just rearrange the order. dy by dx is equal to negative 6x sine 3x squared over cos 3x squared. And if you wanted to, you could turn this into tan 3x squared, but I'm just going to leave it as is. All right, so now those are all the examples I'm going to be covering. Now we'll get into some applications over on this side here. Unrested my space a bit. So the three applications I have, the first is for circuits. So in circuits, if you're given a charge, Q, is equal to 4t plus 6. And then I want to know what the current is of this. So in your circuits course, so that's ECOR 1043, your current is defined as your change in charge, dq, with respect to time. So we just need to evaluate what the derivative of this is. And that would be 4. Because the derivative of this just becomes 4 amps. And the unit for current is amps. So a second example would be for mechanics. So in mechanics, that is ECOR 1046. If you're given a bending moment, M, is equal to 6x cubed plus 12x minus 40, and you want to know what your shear moment is. Your shear moment is the derivative of your moment with respect to your position x. Don't worry if you don't know what moment is. That'll be covered in later term within statics and mechanics. So if we evaluate what the derivative of just this expression is, this becomes 18x squared plus 12. And then a third example of this would be in dynamics. So in dynamics, if you're given a problem, a position essentially, and it varies according to 2e to the t sine t. And then first you're asked, what is the velocity of this particle, of this moving object, something like that. That would be evaluating the derivative of this with respect to time. So this would be your velocity is equal to your change in x with respect to time, change in position with respect to time. So the derivative of this, we have to apply product rule here. So first I'm going to take I'm going to leave the first one the same and take the derivative of the second. So this is 2e to the t cos t. And now I'm going to leave the second the same and take the derivative of the first. That's just going to keep the exact same expression, 2e to the t sine t. And then if this asks me for possibly the acceleration, so this would be evaluating the second derivative. So the acceleration is the derivative of velocity with respect to time, or it's the second derivative of position with respect to time, dx squared by dt squared. So if we evaluate this expression, I'm going to leave the first and take the derivative of the second of this first expression, 2e to the t sine t. And this is all negative sine t. So then I'm going to leave the second and take the derivative of the first, which leaves the exact same function, 2e to the t cos t. So that's the first function done. And now I need to apply product rule again on this second function. So this becomes, I'm going to leave the first and take the derivative of the second. So 2e to the t cos t. And then I'm going to, sorry about that, shouldn't be a circle. All right, cos t. And then finally, I'm going to leave the second and take the derivative of the first. So this is plus 2e to the t sine t. And from that, we can simplify this down a bit. This term right here is going to cancel out with this term. And we're left with 4e to the t cos t. And that'd be our function. So if you want any more practice or see a few more examples, have a look at the PDF document in the link below. And also, if you have any further questions related to any of this stuff, please feel free to reach emlc@carleton.ca. All right, thanks for watching, everyone.